now being recorded. So you have a car on which there is the engine force is pushing it towards the left, and the drag force is opposing that. And the sum of the forces is therefore this summation of forces is F minus the drag force. And we know that this is equal to mass times the acceleration of the car, ma, Newton's second law, which is m times the velocity derivative. So we can write this as F minus CV equals dV dt. mdV dt. Okay, if you collect the terms, you get the differential equation for the velocity of the car. mdV dt plus C V is equal to f of t. Actually, f of f can be a function of time. Now, this is the equation that describes the equation of motion of the car in terms of its velocity. The velocity of the car obeys this equation. It is a first-order differential equation, okay? And then, depending on what kind of force you apply, that is the engine force on the car, you can find the velocity of the car over the time. But this kind of thing is not by itself enough. You need one more thing, which is the initial condition, as you might guess, which is, let's say, v of 0. The velocity at 0 point time, let's say that it is 0. In the beginning, the car has no velocity. Okay? So, this is our equation of motion. We can somehow solve it, but let's try to solve it for different cases. For example, let's say if C equals 0. If there were somehow no resisting forces, we would have and let's say f of t equals f0. That is a constant force is applied on the car. Suddenly you start the engine and it stays that way. Let's see what happens. This is simple. That is meant to be simple. That's why is equal to f0. Now this is solvable. Therefore, dv dt is f0 over m. It is a constant, so that you can solve this for t. You just integrate. It's not a big deal. The derivative is constant, so it is f0 over m times t. The velocity is going to increase without any bound, actually. If you apply a force on the car, engine starts and there is no air resistance or there is no road resistance. This is what you will be getting. This thing will have a slope of, what will that be? If this is 1, this will be f0 over m. The slope will be f0 over m. This is time, and this is velocity. Well, obviously, this is not realistic, okay? This is not what we have in real life. Why? Because we have the resistance of the car developing. As the velocity increases, what will happen? According to this model with no resistance, the velocity will increase up to infinity, which doesn't happen, obviously. What happens is, because as the velocity increases, the air resistance increases, because the air resistance, the drag force is proportional to the velocity of the car, c times v. C being a constant, it doesn't matter whatever it is, but it is a constant. So what happens is, as the velocity increases, the air resistance becomes more and more. Eventually, at some point, the drag force increases to a level which is equal to the engine force, okay? Let me say this. When F drag equals CV equals F of T, or F0, I should say, because it's a constant force, F0, then in our real life equation, you are going to have dV dt is going to be 0, which means that the slope of this curve is going to be horizontal. So what will happen is this, in the real life case, this thing will go like this, and eventually the slope is going to be leveled out, and in this case, at this point, from this point on, kind of, the engine force and the drag force are equal to each other, and the velocity remains constant, which means that the velocity is equal to some v final, which is constant. Okay? So, and from this point on, it doesn't increase. And the region in which the velocity changes is, we call it the transient region. And the region in which the velocity does not change anymore is called the steady state region. From this point on, we don't see a change in the velocity. And as we will be seeing later on, the velocity is going to be V of t is going to be something like this: V final 1 minus e to the t over tau kind of function. It will be a first order function, but this is, we are getting ahead of ourselves. This is not really necessary. This is for later, okay? Don't ask me how I have derived this. We will derive it later on. It will be an exponential growth. So this is what we really do when we model a very, very simple mechanical system. We find the differential equation of this system. And to model mechanical systems, as you all know, we try to write the mechanical systems in terms of some basic elements. So basic, let's say, elements are, basically you have mass, which stores kinetic energy. We have springs, which store potential energy. And we have dampers, which dissipate energy, kind of, okay? So another possible system, another very simple system, which you already know from vibrations or something, is this harmonic oscillator, for example, MK system, in which if you apply let's say, F equals F0, a constant force, what you are going to get will be as vibrations. Now, this system is going to interchange kinetic and potential energy, and what you are going to get will be something like this. It oscillates, well, not a very good drawing, sorry about this, but this will be F0 over K point. Since there is no damping in the system, this is T, and this is the position, X is the position let's say, position of the mass of the system. And the equation of motion that describes this system is mx double dot plus kx is equal to f of t, as you probably know from other courses. So, in order to model mechanical systems, we use these kinds of elements, simplified elements. And as you can guess, all mechanical systems cannot really be modeled by, masses, springs, and dampers only. There are, of course, other elements, but we try to get to the basics of modeling and try to show you the, simplified models. Otherwise, usually there are other things which are a bit more complicated. We will get into them later on. So let me just briefly talk about all these elements. The mass element, for example. As you know, the equation of motion that describes is F equals ma, which is mx double dot. And there is the possibility of rotational mass or rotational inertia. T is equal to I alpha, which is I times theta double dot. This is the rotational equivalent. Rotational inertia, if you like. Okay, this is the translation. Let me just try to draw this. So you apply a force on this mass, and the displacement is x, whereas here you have suppose that this is a circle, okay? You apply a torque on it, T, and this thing rotates with a theta, okay? And it has an inertia, mass moment of inertia of I. Let's say that it is fixed about this point. The kinetic energy of this system is 1 over 2 mv squared, which is 1 over 2 mx dot squared. And the kinetic energy of this system, the rotational system, is 1 over 2 I theta dot squared, as you can see. And if you have a rotational plus translational system, it will be a combination of both kinetic energies. It might have 1 degree of freedom, 2 degrees of freedom, etc. Okay. The damping, let's start with the spring first. The spring element. Well, obviously, the spring is something like this, as you know. This is, which we show by K. There are real springs in real life, but when we say spring, we don't really mean a spring. We say something with an elasticity, that is, something that has the capacity to deform. For example, if you have let's say a rod like this, from strength of materials, if you pull it with a force like this, let's say, which has a length of L, okay, it has the capacity to deform. We know the basic equations, so let me just very quickly derive it. We know that, for example, the stress is equal to modulus of elasticity times strain, and the strain is delta L over L, okay? And therefore strain is like sigma over E, which is F over A, force over the area over E. So we can say that from here, the deflection is equal to FL over AE, right? So you can say that F is equal to AE over L times, what will that be? Over L times delta. And if now this is actually F equals K times delta X, if you like. We know that this is F equals Kx is the describing equation. So we can call this thing our spring constant K, and this will be our X. So the spring constant of this system, for example, is AE over L. The spring constant or the stiffness of this system increases with area and modulus of elasticity, and it decreases with it's inversely proportional to the length of the rod, for example. So, for example, a rod can be modeled as a spring for the purpose of, let's say, modeling. Otherwise, for example, if you have a beam in bending like this, let's say this is F, okay. Let's say that this displacement is X. Again, you have L, etc. Okay. Again, from strength of materials, we know that this is 3EI over L cubed times X. Okay. So that our spring constant in this case will be this quantity. This will be our K. So we can find the spring constants of different systems through modeling. As I said, the real springs are not that common. They are possible, but the spring modeling is applied to all sorts of systems who have the capability of deform and can store potential energy. The potential energy that is stored in a spring is 1 over 2 kx squared, as you know. And also we have the rotational springs, which store rotational energy, and we model them. Well, we sort of draw this kind of figure. Let's say this is theta 1 and this is theta 2. And usually the torque applied to this thing is K, the torsional spring constant, Kt times, let's say theta 2 minus theta 1, or delta theta is the rotational spring constant. And here the kinetic energy will be again 1 over 2 Kt theta 2 minus theta 1 squared. Sorry, not the kinetic energy, it's the potential energy. Potential energy in the spring. Okay. Dampers, dash pots, dissipators, etc. are modeled by this kind of a figure. Well, we assume that these are energy dissipators, okay? Let's say this has a B1, this is B2. Let's say that this is C or B or whatever. What do we use? Let's say that so the force that is applied here, F is equal to B times, let's say V2 minus V1. Okay. And the energy dissipated I say the power dissipated, or I should say power dissipated, not energy, because energy is the integral of that. Power is minus B times delta V squared, or let's say V1 squared. Okay. So we now come to our very basic. What is going on here? Why do I press control? I don't know. Oh, okay. So we get to our very basic mass spring damper system, this one. Which is the standard system used in vibrations. Let's say this is f of t. Let's say this is x. The equation of motion is derived from Newton's law, which is there is this force here. There is the spring force, which is kx. There is the damping force, which is bx dot. Okay, this is m. And this is equal to mx double dot. So the real forces are equal to the inertia force, which is the following: F minus kx minus bx dot is equal to mx double dot. Therefore, we get mx double dot plus bx dot plus kx equals f of t as our equation of motion. This is the differential equation that describes our system for all conditions, for all forces. Solving this, we can find out how our system behaves. For example, for this system, if you have a, let's say, a certain force, constant force acting, it will be, if B is 0, this is what we are going to get, as I have said. This is for the case with B equals 0, no damping. If B is not 0, you are going to have oscillations, but eventually those oscillations are going to die out. This is B greater than 0. Okay. If, by the way, if f of t equals f0. By the way, I'm going without letting you ask any questions. Are there anything you didn't understand up to here? It's pretty basic up to here, more or less. So I don't assume you have too much trouble following it.
Hocam, can I ask a question?
Yes, I
Hocam,
cannot hear
when
you. I don't
can you
hear
hear
you.
me?
Janar, are you asking something?
Yes, hocam. I would like to ask a question.
Just a second. I think the voice is very low. Yes, go ahead.
Hocam, when b is equal, b is bigger than the zero, in the end it will be constant, right? The velocity. I mean, how can I say? The velocity will be
Condition
zero.
is going to be, it's going to settle down to position, a steady state position, yes.
Okay, thank you so much,
But the
hocam.
force is a constant. It is with a constant force this happens. Okay.
Okay, hocam. Thank you so much.
Yeah, if B is, for example, negative, then it means that the B is adding energy to the system, so it will be an unstable system, on the other hand. Okay, now we will do a trick here, which we will be using a lot in this course, actually. We will use an operator. We will let the derivative operator by derivation, I will replace it by an operator called S, which, as you can guess, is the Laplace transform operator, but I will introduce it early here. So that, for example, dx dt, which is x dot, will be equal to s times x. Okay. On the other hand, d squared x dt squared is the second derivative, which is x double dot, as you know, in our notation. This will be s squared times x, second derivative. Okay. Now, this is exactly what the Laplace transform does, but we can convert our differential equation to an algebraic equation if you use this S operator, which is the Laplace transform variable, as we will see. But let's do it now. In this case, if you use this S operator, we will have m x double, that is s squared x, plus b sx plus kx only, because it doesn't have a derivative, is equal to f. And here we can convert our equation to like ms squared plus bs plus k x is equal to f. And we can find the response of this system, well, rather write the equation of this system, x over f, as the following. 1 over ms squared plus bs plus k. Okay. Now this representation is the same with the representation here. It is the same thing, only in a different written in a different form. This is an algebraic equation. This is a differential equation, but they represent the same thing. And actually, this is called the so-called transfer function of this system. For this system, let's say between x and f. X is the output, f is the input, and we usually show this thing by the following graphical representation. You have f coming in. F is the disturbing force that makes this system move. X is the thing that is the output, and you have 1 over ms squared plus bs plus k, which is our transfer function, which represents our system. As you see, we can find how this system moves accordingly. Well, we represented the system without the transfer function. For example, for the car system, as you remember, we had the equation was mv dot plus pv, sorry, it was cv outside, cv was equal to f, right? In this case, again, by using the Laplace transform variable, you will have ms plus b v is equal to f. So v over f, let's say these are variables not of time but of s now, 1 over ms plus b. For the car, this is the transfer function. Between the velocity and the force. Okay. Yes.
Where did the B come from?
B, sorry, it should be C. I'm sorry. Okay. All right. One more a very simple example. Let's say that it looks sophisticated, but you will see that it's very simple. Let's say that you have a robot arm, a 1 degree of freedom robot arm, which I will try to use in this course. Let's say that you have a mechanical arm like this, which is a simple beam-like thing. Okay. Now this is an arm that can rotate. So it has this is the rotation theta. Okay. Now this is connected to a shaft, let's say, and this shaft is connected to a motor like this, and this motor applies a torque on this robot arm. Actually, it is a robot. It is an arm that rotates from one point to the other point by applying a torque. This arm has a mass moment of inertia of J, let's say. Okay. So the equation of motion describing this arm, although it looks complicated, it's very simple. It is simply the following. The torque applied on it is equal to J times theta double dot. Okay. This is the, well, we assume no resistance, no spring effect or whatever. So this is the equation that describes the system. So we can write it in terms of theta double dot can be written as s squared times, let's say, theta of s, if you like. So that you can say theta of s over t of s is 1 over js squared. Okay. For example, this is the transfer function between the input, which is the torque.
Hojam, okay, can you just say again what J represents?
What? G?
The J in
J,
T
okay.
equals J theta double.
Yeah, it is the rotational inertia of the arm. Okay.
Yes, thank you, Hocam.
So let's say this is 1 over JS squared is the thing. This is called the block diagram representation of this system. T of S is our input, theta of S is our output, and the thing that multiplies the input to give you the output is the transfer function. So you can write, for example, theta is equal to, or I should say theta of S is equal to 1 over JS squared times T of S. As you see, output is equal to input times the thing that transfers it to the output, okay? So this is the output. This is the I don't know why. And this is the transfer function. Let me just write it in shorthand. Something is wrong here.
Hocam, I think I missed the part that you said, what is J? Could you please explain it again?
Yeah, sure. Just a second. Because the mass moment of your rotational inertia of the arm, that is, for example, when you apply a torque on an object, torque is equal to I times T, we said theta double dot, right? And this is exactly what we mean by that. Okay, we used I before, now we are using J. For example, for this system, if you have let's see what happens, for example. You will have J theta double dot will be equal to T0, right? So theta double dot will be T0 over J. Okay. So you can integrate this twice. Obviously, not all differential equations are this simple, but theta of T is going to be something like T0 over 2J T squared plus C1T plus C2, let's say. And if theta initial conditions are that theta 0 and theta 0 dot are zeros, this will give you C1 and C2 equals zeros again. So you are going to get, for example, the theta of T is T0 over 2J, which is a constant, T squared. So this will be a parabola T versus theta, which will be like this, or this is not really like it. It's like this. So it just keeps on increasing if you apply a constant torque on this system. Okay. Now, in the control problem, if you have a robot arm like this, an arm which you want to rotate, you don't obviously apply a constant torque on it. Maybe a constant torque would make it just rotate like crazy. What you want to do is, well, for example, we would like something like rotate some degrees like theta, let's say 1 equals, let's say 90 degrees, and stop. This is very typical. You have a robot arm like this, you want it to rotate a little bit and then stop. Okay? This is how you should do it. You are initially at, so initially you have theta of 0 equals 0 degrees, and theta dot of 0 is 0. And finally, let's say theta of 0, sorry, theta of t, whatever, is 90 degrees, theta of t1, let's say, and theta dot of t1 should be 0. Okay? So the theta should be you start from here with 0 velocity. You should do this as quickly as possible. Come here and then stop. Okay? This is theta 1, which is, let's say, 90 degrees. Well, how do you achieve this? How do you do it? It looks easy, but it's not very easy to do this. Okay, you basically have to apply a kind of a feedback control scheme here in order to kind of to regulate the torque that is applied on this system. Okay. Basically, we do something like this. This is our this is the torque that is applied, and this is theta, and this is, as you know, it's 1 over j s squared box. Okay, we measure theta by some sort of measurement. Okay, and then you have the motor. Well, let me just draw it better. You have the motor that provides this, and then the motor is driven by the controller, which we will come to see. And here, what you do is you measure the theta. This is theta. Compare it with the theta, let's say, the theta value you want, theta 1, which is the theta reference. Let's say this is the 90 degrees. And then this is the error that drives your controller. And the controller sends a signal to your motor. And the motor generates the torque to drive let's say, the arm. And the torque you are going to apply is going to be something like this over the time, if you can eventually find it. This is the time, this is the torque. It will start from here, it will be something like this, but then it will be kind of be 0, okay? Eventually, for your, well, my drawing is not a very good one, but its shape will be something like this. Okay, this is the torque applied by the motor, has to eventually come to a stop so that the position of the, let's say, arm is going to stay constant. Okay, that is a kind of a simple control problem. But in this, single hour lecture, I tried to introduce some basics of mechanical systems and their control. We will continue the next time. Okay, so let me stop the recording.